car wheels in general are very important when it comes to drag. And when we get to semi-trailers, that is just as true, and maybe even more so, because you not only have those single wheel configurations, but also the double wheel configurations. And in fact, wheels typically account for about 30 to 40% of the drag of a car. And things get even more interesting when you consider the different sections of a wheel. So you obviously have the rim, but then there is also the tire, as well as the tread on the tire, like the longitudinal grooves and the lateral grooves, and even the wheelhouse packaging. And understanding how all of these things affect a wheel's drag is the first step to reducing it, which is obviously a good thing because you can save fuel and then you can use that fuel later to create bonfires or whatever. Anyway, so to look at how a truck wheel's rim and tread affects its drag, we're going to look at a paper called Experimental and Numerical Investigation of the Aerodynamic Ventilation Drag of a Heavy-Duty Vehicle Wheel. And this is a cool paper to me because in the sense that the researchers are not only looking at the typical one wheel configuration in a car, but they also have the double wheel. And sure, the one wheel configuration is quite interesting because you do have some trucks with that at the front as well, but the two wheels stacked together is also quite interesting because we don't see this too often. So we're going to be seeing some results that we don't really come across very often. So this paper is also quite interesting to me because they seem like they really try to do a lot of things in this one. So usually the best approach to a paper is to focus on one specific thing and just make the entire paper about that. Here, they're not only looking at the wheels, like the rims and treads, which are also really interesting, but also at the CFD setup to look at this, as well as the ventilation drag, which we'll actually get to in a second. The ventilation drag is something that we don't really cover very often, mainly because it's so difficult to measure. So the question is, what is ventilation drag? It's a fairly common term, but it refers to, it's a fairly uncommon term, but it refers to something that can seem like a phantom drag because we can't really measure it in a regular wind tunnel. So to describe to you what it is, consider a regular car. It has four wheels, hopefully some have been stolen, but anyway, four wheels. And as you are driving along, the air hits them and creates this force backwards on them. We all know that to be the drag. But the plot thickens when you consider the spokes of the wheels, for example. You see, as the spokes chop through the air, sure, there is a backwards force on them that contributes to the overall drag of the car, like the air is trying to push back the spokes at the top of the wheel so that the car is has some resistance going forward. But there's also a moment created on these spokes because if you think about the spoke at the bottom of the wheel, as it rotates back to the back of the car, like it rotates back up, it's actually going with the flow at the bottom. So the drag that it produces should be minimal, especially when you consider that the farther away you get from the axle, the greater the distance is, and hence the greater the tangential velocity of that spoke at that point. Hence, they'll match the free stream velocity and potentially even exceed it in some points when you have a wake. So when you have like the front of the wheel, there's some weight coming off of that, and it's hitting the spokes at the bottom of the wheels. These spokes here are potentially going to be moving faster than the flow hitting it. So in theory, you actually have the spokes traveling faster, and then the air is in front of these spokes is actually stopping it from moving backwards. So it's actually stopping the wheel from rotating at this point. And that results in this moment that's effectively resisting the wheel to rotate, and that means that the car has put more force into the wheel, more moment, to get this wheel to rotate around. And that is something called the ventilation drag. And that comes about because even though this spoke is being forced forwards by the air behind it not getting out of the way in time, that actually makes it harder for this engine to push the car forwards. And so we can now expand our focus from this one point on the spoke that is traveling faster back than the flow around it, and think about the spokes in general as they go around. These spokes are chopping through the air, and even if they are chopping down, the backwards force on the spokes is negligible because the pressure acts perpendicular to the surface, and the spoke surface is parallel to the direction of the travel at this point, so there can't actually be any backwards force or any drag on these spokes when they're completely parallel to the ground. But because the spoke is struggling through the air, that creates more resistance for the engine to overcome, and hence it is kind of like a drag. And because of air, it is in fact a drag, and this is what ventilation drag is. And that is one additional factor that we'll be considering today. And ventilation drag comes about not just because of these spokes, but also because of the tread, which we'll get into later on this podcast. So let's jump into the researchers' methods to see how they investigated the effects of the rim, tread, and number of wheels on the drag and ventilation drag. I should also mention that measuring the ventilation drag is quite hard to do. One common method is to is to see how much load there is on the units driving the wheels in the floor. Another method is by putting torque meters in the axles that connect to the wheels to see how much moment is being produced. So now let's move on to the methods. So they used both CFD and experiments, which is good because when done well, they complement each other. And first of all, they used a 1 to 4.5 scale model of something they term a heavy-duty vehicle. Figure 1 here shows this vehicle. It is a half model with only the left half of the vehicle modeled, and then there's this splitter plate going down the halfway point. And that definitely introduces some limitations because the periodic vortex shedding nature is not captured. But for a general idea of how the wheels affect the drag, this is an okay approach. So the reason why they might have gone with this model could be to get a higher Reynolds number with a larger model, or it could be to reduce the number of cells they needed in their CFD with only a half model here. They say that this vehicle develops a flow topology in the vicinity of the wheels that is comparable to a real commercial vehicle. I'm not really sure how comparable it is because they don't give any numbers or figures, but as a general approach, I guess it's okay. I mean, to be perfectly honest, there are so many different types and shapes of heavy vehicles that it's not so much that this vehicle approximates a typical heavy-duty vehicle, but rather that there isn't really a typical heavy-duty vehicle when you think about it. So this geometry is fine, I guess. Like, there are also different types of heavy-duty vehicles. So this is just a generic type, I guess. Now, one thing that stands out is the blockage ratio that I mentioned. So for this model in a wind tunnel, it is 7.8%, which is quite high. I mean, because they have a 3/4 open test section, which actually I think in figure 4, if we scroll down, here we go, we actually see this test section here. We have the 3/4 section open test section. And for something like this, the upper limit is about 15% blockage ratio, but once you start getting above about 10%, the correction factors are so high that you can argue that the results really aren't that valid anymore anyway, because the flow physics has changed so much. But even it's still at 7.8%, that means you need to have quite a decent amount of correction. And obviously you can actually get a higher blockage ratio in a 3/4 open test section than a completely closed test section. And for those of you who don't know, the 3/4 test section means that you just have one surface is present and the other 3 walls around the test section are not, as we see here in this figure. And so with this model, as I mentioned, they have a 1 to 4.5 scale model. If they went even bigger to something like a 1 to 4 scale model, then the blockage ratio would be really high. They also say that their goal was to achieve a fully turbulent boundary layer at a Reynolds number of 300,000. So that is also one of the reasons why they went with such a scale here. Now, to test the different rim designs, namely the 3 different ones in figure 4, if we scroll up here, these 3 different rim designs, they used a modular rim design where they had effectively the base rim, and then they could just add additional parts to it, as you see here in figure 2. They then have the typical truck rim, which has this raised center, as we've all seen on trucks. They then have something called an eco rim, which is when you have the flat, like the rim is actually flat instead of like poking out, and that has only a few openings, probably just for the cooling flow. That's about it, I'd imagine here. And then they have a completely closed rim, which usually achieves the lowest drag, and we'll see in this investigation if that is also the case. My money is going to be on that. This is going to be the lowest drag rim. So they also tested 2 different tread types, 2 different tread patterns. The first one in figure 3A is just this longitudinal groove, and the second one is with the lateral grooves as well. So you have the longitudinal grooves and the lateral grooves. And this is what I mentioned earlier, where they're trying to do so many things in this paper. In my opinion at least, they are not only ending up with different rims, different treads, different like ventilation drags, CFD setups, and by trying to do everything in one paper, you usually do nothing that well. And I mean, usually you just have one different type of rim design or different rims to test, and then one different tread or different tread patterns, or you just focus on the CFD method, not all of them at once. So that results in a lot of questions being called up about the results. But anyway, in figure 3, this shows the tread patterns investigated, and with the longitudinal grooves, they are the grooves that go circumferentially around the tire, and then the lateral grooves are the ones that go like across the tire, and they sort of connect the inside parts of the tire to the outside parts. And in fact, one of the hardest things to do when it comes to the groove pattern aerodynamics is to somehow characterize them properly, and that is because there are more tread patterns than you can poke a stick at. I mean, if you go into any car, like a mechanic or something, you will see so many different types of treads. So you have like these lateral grooves at different angles. You have them with different depths. You have different widths of the lateral grooves and long-term grooves as well. And then on top of that, you then have to consider how the geometry changes when the wheels are also rotating, because as the wheel rotates, the rubber, which is elastic, deforms and starts to stretch out in diameter and then shrink in width. Then you have the wear and tear aspect on the tires, where people are driving around with all different levels of wear and tear on their tires. So there are so many aspects to consider when looking at tread patterns and the effects of them on the aerodynamics, which makes it really hard to do. In my opinion, it's probably the hardest thing to do on cars in terms of aerodynamics at the moment. So anyway, we can see that there are 2 different tread patterns here on 3 different rim designs, making a total of 6 different configurations. Now, the authors say that the experiments were conducted in the model scale wind tunnel at Stuttgart University, which we saw in, I think it was figure 4. They then say that the wind tunnel features a state-of-the-art setup, including a 5-belt system. For those of you who don't know, when you simulate wheel rotation, the best way of doing it is to use a moving floor, and that is achieved by using these belts that are driven on the ground underneath the car. In figure 6, if we scroll down to that, we can see one of the wheels on one of the belts just here. It's a little bit hard to see, but just underneath this contact patch is literally where you have this moving belt. It's usually like this sheet metal that goes around. And this particular belt system is called a wheel drive unit because it is the unit that drives the wheels. So wheel drive unit. Anyway, a 5-belt system is where you have one belt under each tire and one large belt underneath the car's underbody between the 2 tires, like the left side and the right side. And the belt extends from a little bit further upstream than the start of the car, all the way past the rear of the car. So why do we have these 5 belts? I mean, it is obvious that we need one belt for each wheel, but to drive them, but we want to drive the underbody as well. Like, why do we have this large belt underneath the underbody? Well, this is to make sure that the boundary layer grows there in the right way, or at least actually it doesn't grow. So the reason why this is important is because if you imagine a car driving along, well, the car moves along the road, but there is no relative motion between the air and the road unless you have a gust, of course. But let's say it's a still day. There's no relative motion between the air and the road. It's the car that is moving. As such, no boundary layer forms on the road. But in a wind tunnel, we accelerate the flow and the ground is stationary, so there is relative motion between the air and the ground. This relative motion will create a boundary layer, which is exactly what we don't want because that doesn't replicate the real life conditions. So the large belt underneath the car is there to stop there being relative motion between the air and the ground, because the ground there, which is the belt, is moving at the same speed as the free stream air. Hence, no boundary layer forms, at least generally speaking. If you have some wakes and etc., that affects the boundary layer, that affects the ground, but that is also somewhat true when you're driving along. Now, you might be thinking, well, what about upstream? I mean, air is coming from there and there is no belt there yet. The belt only starts as we approach the car. And that is true. And that is where the boundary layer control system comes into it. Now, this is a complex system that I could do like 5 podcasts on because it's quite complicated, but I'll just run through it quickly here. So here is the crash course. The boundary layer control system consists of the following. As the contraction reaches the test section, there is a boundary layer scoop that cuts off the boundary layer and diverts it away from the rest of the test section. As such, only the free stream flow reaches the test section's ground. So at the start of the test section, the flow is the same free stream velocity as when you go up into the middle of the flow. That's what's on the ground. As the flow flows along the ground towards the car, a boundary layer does grow. But just before the car, there's a suction system. And this is literally a bunch of holes in the ground that sucks the air in. And that ideally gets rid of the boundary layer so that now the only air hitting the belt is the free stream flow. Now for the 5-belt system, things get even more complicated because there are no belts between the front left wheel and the rear left wheel, or between the front right wheel and the rear right wheel. So literally between the 2 wheels, like the upstream wheels and the downstream wheels, there's just regular floor. It's not a moving ground. As such, a boundary layer can grow in each one of these regions. So to stop that from happening, at least ideally to stop from happening, there are things called blowers at the rear of the front wheel drive units. These blowers literally blow free stream air velocity behind the front 2 wheels to overcome the boundary layer that would usually form there. Then behind the rear wheels, there is no belt between them, like between the rear wheels and the rear of the car. And that means the boundary layers could grow there as well and affect the diffuser. So to overcome that, blowers are also used at the rear of the rear wheels, the rear of the rear wheel drive units to overcome that boundary layer too. So the boundary 3-layer system is just what I mentioned there in a nutshell. Now, as I said, I could go on a lot about this and the difficulties associated with them, but that would have to be for another podcast and many other podcasts. Instead, I want to focus on something they say here, and that is that this facility that these authors are using, which has a 5-belt system, is state-of-the-art. Well, a 5-belt system is not state-of-the-art, actually. A 1-belt system is, and that is where the entire car just goes on one big belt. That is state-of-the-art. In fact, you could even argue that a 3-belt system is even better than the 5-belt system, because now there is the technology to measure the forces on the wheels through even a 1-belt system. So technically, a 5-belt system is not state-of-the-art. It's good, but not the best. But anyway, let's move on. Now, remember how we were talking about the ventilation drag of the wheels measured? Well, measuring them directly is quite hard, and those researchers didn't do that exactly. Instead, they measured it coupled with the rest of the wheel drag, which is still pretty good. Like, you don't come across that too often. So in figure 5, which we see here, we see the load cell setup in this right side here. Usually the red struts are what connects the car to the load cell underneath the floor. So these ones come through down here, and then you can measure the forces on the entire car. However, the problem with that is if you want to know what the ventilation drag of the car wheels is, that is the force that is determined by the wheel drive units and effectively how much you have to drive these wheel drive units. And that is an internal force. So you don't get to know that through the normal setup that we have here. So in order to add the ventilation drag to the overall drag of the wheels, the researchers secured the car to the wind tunnel with these red struts, which would usually be connected to the load cell. And instead, they connected the wheel drive units to the balance. That way, they could measure how much force the wheels were putting in, to the wheel drive units, and as such, the ventilation drag as well. So to do that requires a lot of work to change the setup. Like, this is a very complicated and sophisticated setup, and just to change this takes a lot of time and work. And it can even be a risky thing to do as well, because these load cells are incredibly sensitive, and if you start changing things, there's no guarantee that when you put things back to how they were, you're going to get it right and the uncertainty will be different. But anyway, these researchers went to great lengths to do this, so that's pretty impressive. They say later on that the uncertainty in the load cell is plus or minus 0.1 newtons, which is quite low. I'm not sure if that is 95% confidence interval or not, but I'm guessing that is so, because that's usually the standard for these load cells. So in addition to the forces that they took in this setup, they also took some PIV measurements, which gives us some really interesting results, and we'll see them later on. And the PIV laser that they used was an ND-YAG, which is like the most common laser ever. I mean, it's pretty good. It gives a green laser, but it gets boring after a while because you almost never see a non-green laser. You never see a blue laser or a red laser or an infrared laser, which you can't see anyway, but still it would be nice to be able to imagine that you'd be seeing it. You only ever really see green, and I just don't want to exclude any other colored lasers. I mean, all are welcome, and we should make a greater effort to have different laser colors. Anyway, they took the PIV laser sheets around the front wheel, which we are showing in figure 6 here, in these 4 sheets here. So let's move on to the CFD setup, because they use a Lattice-Boltzmann method solver. And if you don't know what a Lattice-Boltzmann method solver is, also known as LBM, they are the main alternative to Navier-Stokes solvers at the moment. So Navier-Stokes solvers are by far the most common CFD solvers, but Lattice-Boltzmann is becoming more and more popular because it is a much more efficient approach when you have multiple cores. And that is because of the type of information that is shared between the cores and how much information is shared. So I won't go into that because we've gone into that quite a bit in some other podcasts, in podcast number 85, 86, 91, and 92. So if you want to know more about LBMs, check out those podcasts. Anyway, this setup is mostly what you'd expect, except when you get to the wheels. So simulating the wheels has been the bane for automotive aerodynamicists for a long time. And even still, there isn't an accurate way of doing it. In fact, the most promising way is a way that these researchers here have done, but from what I can tell, they didn't need to use this method. So let me explain what I mean. So these researchers used a sliding mesh on the rim, which is quite standard practice, and this means that you have each rim kind of in its own little domain. It is completely circular, by the way, and then each time step, this little domain actually rotates by the right amount to correspond with the wheel rotation. And this is completely fine. That is, as long as you get the meshing at the interface right, which only happens if you have a fine enough mesh. Otherwise, you get some mismatching here between the local domains and then the global domain. But anyway, it is simple enough, generally speaking. So as for the side walls of the tires, they have a wall boundary condition, rotating wall boundary condition, which is also good because for this purpose, because these walls are smooth. And what that means is that there's a tangential velocity which is applied to these walls, and that simulates the rotation of them. And that is fine too for this particular approach. Now we get to the good part here, which is how they simulated the tread. So to do this, they use a method called the immersed boundary method. And this is really cool, particularly for simulating fluid structure interactions. So for a fluid structure interaction, is what it sounds like. It is where you have a fluid and a structure interacting, and usually one affects the other and vice versa. So in this particular instance, using the immersed boundary method for the tire is very good, and it's, in general, it's very promising because the tire deforms not only as you spin it, but as it reaches the point on the ground, the contact patch, it then touches the ground, it has this loading on it, so it deforms, and as a result, there is this bulge that forms. And then as it rotates back up, the tire gets like pulled and stretched. So there's quite a bit of deformation going on in this tire throughout the entire rotation cycle. Now, if you were to use the sliding mesh approach, which has been the typical approach for simulating rims here, we could actually simulate the bulge. We couldn't actually simulate the bulge because as the tire rotates around, the deformation begins, and then when it lifts off, it doesn't. So there is no axisymmetric thing going on here. But here they don't have the bulge happening, and this is because they have a rigid tire. So the immersed boundary method allows for this deformation to occur because the way it works is if we effectively have two grids on like this domain, and one, like when the solid deforms, it tells the other grid, hey, this is actually fluid in this region now. So you use the fluid equations instead of treating this as a solid. And then when it becomes a solid again, it goes, okay, I'm now a solid again. So at these points, we're going to use the solid equations and not the fluid equations. So the immersed boundary method allows non-axisymmetric objects to rotate and even change shape. Now, in this particular case, as I mentioned, these researchers have chosen to use this IBM method here, this immersed boundary method here, but the tire is not deformable. So I don't see why they decided to use that method instead of just putting the entire wheel in the sliding mesh method, because the sliding mesh method will handle a axisymmetric tire as we have here. But maybe it worked out to be less computationally expensive for them because they had fewer cells rotating, which is inherently quite taxing. Or maybe they were having problems with the sliding mesh meshing the ground. I don't know. Anyway, for a normal car tire with deformable tires, this immersed boundary method is sweet. But for this particular case, from what I can tell, it's not really needed here. But anyway, it's cool to see, just see it in application. So the CFD that they used was very large eddy simulation, which is similar to large eddy simulation, LES, except instead of being large eddy simulation, it is very large eddy simulation. And one thing that is important to note is that they said that the simulation domain is created with dimensions large enough to avoid any blockage or interference effects. Now, to me, while this sounds cool, it's not actually a great idea here because they should be making the CFD domain match their wind tunnel domain. Otherwise, you really aren't comparing the same thing. When you use your validation data from your wind tunnel, your validation data corresponds to a different setup to your CFD. So the wind tunnel setup places certain conditions on the setup while the CFD is placing other conditions. So they're not the same. That can and usually does lead to differences in the results from the experiments and the CFD, which means that when you're trying to validate your CFD, neither are actually wrong. It's just that they're looking at different things. And I should probably mention here actually that if you want to get better at CFD, take one of our courses. We have them for intermediate, beginner, and even how to use OpenFOAM. And you can find them in the link below. So anyway, let's move on to the validation part of this CFD. Now, the CFD and experiments, I presume, were carried out at the free stream velocity of 60 meters per second. That's what it seems like they're saying. And at a reference number of 300,000, which is the desired one that they wanted. And for a full-scale equivalent, they said for the heavy-duty vehicle, that is equivalent to a 50 kilometer per hour speed. That's as I said here. So table 1 shows a comparison between the CFD results and the experiments for the single front wheel. So remember, we get to see the double wheels at the rear as well, which are given in table 2 here, or as the French say, table 2. But now let's look at the single tire. So the wind tunnel results show that making the rim flatter, so going from this like three-dimensional popping out rim to a flat rim and a completely closed rim here. So going from the regular rim to a flatter rim, and then even closing it, reduces the drag, which is good because that is what we see in a lot of different papers. But when we compare the tread pattern, we see that incredibly, adding the lateral grooves greatly increases the drag. I mean, with just the longitudinal grooves here on the left, we see drag of about 0.37 newtons, and for the same rim, but now with the lateral grooves here, it's now up to 1 newton. So it is a 170% increase in the drag, which is about what we see with different rim designs as well. So if we go from the grooved eco to the treaded eco groove close, it's all about the same, about 170% increase in the drag just by adding lateral grooves. So the addition of lateral grooves, and I assume here that the longitudinal grooves haven't changed to these ones here, so it's just the lateral grooves that have been added, the drag more than doubles, it almost triples. And even if the longitudinal grooves have changed, still the fact that the tread can make such a difference is unbelievable. I don't believe it. However, there is maybe a good reason as to why lateral grooves make such a big difference to the drag, and that is that they change how the flow goes around the edge of the tires, also known as the shoulder of the tires. And this greatly affects whether the flow remains attached or separated. So there is reason to believe that perhaps these small additions can greatly affect the drag, and we will see a little later in the PRV results to see if they did indeed affect the flow separation pattern or other flow features as well. And later on when we go to ventilation drag, we'll talk about this a bit more as well. But first, let's look at the CFD validation, because in table 1, we also have the CFD results for these very same wheel configurations. So the good thing is that for the wheel with just longitudinal grooves, the CFD is quite close to the wind tunnel results. The CFD gets the general trend right of when you close the rims, or get them smoother as well, the drag drops. But there is a fairly consistent 10% error between the CFD and the experiments. This is almost like a systematic error, we can say. If we go to the wheels with the lateral grooves, we see that the CFD starts to perform much worse. The trend of the drag dropping with smoother and more closed rims isn't present here, like it goes down and goes back up. But it does capture the trend of the drag jumping up a lot between the longitudinal grooves and the longitudinal and lateral grooves together. So that is, I guess, good to get. But to be perfectly honest, I don't know what the exact problem is here. There is some parts I get right, other parts I get wrong. I do have a couple ideas as to what is wrong with the CFD, and the possible reason is that the mesh isn't fine enough. That's one reason. And I mean that there is no mesh independent study here, or even a time step independent study here. And because we're dealing with quite fine details, and in this case, the lateral grooves, obviously the fine details do affect the results substantially. Perhaps the mesh isn't fine enough in this region. That is one possibility. The other possibility, which I am a little more confident in saying, is that it is caused, this error in the CFD is caused because it doesn't include the wind tunnel test geometry. So as I mentioned, this is a 3/4 open test section, and what that means is that the flow coming out of the contraction is typically going to expand in cross-sectional area as it expands to equalize the static pressure in the free stream flow compared to the barometric pressure in the surroundings. As such, the streamlines in the flow won't be completely aligned with the hoped for free stream direction. They'll be a little bit skewed. As such, the streamlines hitting the wheels in the wind tunnel and the car in general will probably be different to the CFD. As such, the flow around the wheels will be very different, including the separation around the tire shoulders. So maybe both of these reasons for the meshing and the different test sections are why the CFD is off. Maybe one of them is the case and the other one isn't. I'm not too sure here. We don't have enough results at the moment. And also, of course, perhaps the atmospheric conditions they used in the CFD weren't the same as the wind tunnel. So for example, perhaps the density of air wasn't the same between the two because of different barometric pressures and humidities. I didn't see anything in this paper about calculating the density of air in the wind tunnel, especially considering that we use them for the CFD as well. So the density in the wind tunnel could be different to the CFD, and that could give a couple % error quite easily and lead to these errors seen here too. And I should also mention here that if you need a new instrument to measure the density of air in your wind tunnel, check out the AMSI Hawk. It's the one that we make in the link below, and you'll be amazed at how much more accurate it makes your experiments, and it's like makes your CF your research, you find so many more things. It's amazing just how many problems the density of air can create if you don't get the right density of air measured. So anyway, I think we have a few likely reasons why the CFD here isn't agreeing that well with experiments so far. But let's move on to table 2, because this table now features the double wheel configuration, which I'm quite looking forward to seeing the results of. I don't get to see these too often. Now, for the wind tunnel results on the top line here, we see some pretty interesting trends. So for the tires with just the longitudinal grooves, we still see the typical drop in the drag when we smoothen the rims, but we see that the closing the rims only helps to some extent, and going from mostly closed to completely closed doesn't really do anything for the drag for the longitudinal grooved tires. This might be just because having the double wheel greatly reduces the flow coming through the rims anyway, so there's a bit more blockage here. So closing it mostly is not really going to be yielding that much difference to completely. However, when we put the lateral grooves on, we see that the old familiar trend where closing the rims more and more always reduces the drag. Why this is? Well, they don't give any flow vis below on it, so we've been left high and dry on that one. But my guess would be that with the lateral grooves, the separation is affected around the shoulder, and maybe that pulls more air through the rims and makes these rims play a larger role. Anyway, that would be my guess, and maybe some things we weren't meant to know yet. I mean, you don't give everything away on the first date. Leave some surprise for the next one, am I right? Anyway, what we can see is that for this double wheel configuration, adding lateral grooves also greatly increases the drag, but not as much as for the single wheel. So remember, in the single wheel, when we added lateral grooves, the drag increased by 170%. Here it's only about 70%. That is likely due to the inside wheel not really being affected as much by the lateral grooves as the outside wheel. I mean, the inside wheel of the double wheel setup is not exposed to not a lot of fast moving flow. So the grooves probably won't have as much of an effect because they just don't have the flow to work with. That is my guess anyway. Now for the CFD here, it is mostly all over the place. I mean, yeah, the general trend of closing the rims reduces the drag is present, but the absolute values are quite wrong, and then the amount that the drag drops with the closing of the rims drops by the same amount, again about 10%, but the absolute values are also different, and the relative differences are similar. So it's all over the place here. Then with the lateral grooves, the closed rims, the closed rim trend tends to hold less, and the amount the drag changes isn't the same. So I think when it comes to the double wheel configuration, the CFD isn't really trustworthy because I just don't know what is good and what isn't. It's a kind of higgledy-piggledy. So overall, I would probably score the CFD on the single wheel maybe a 6 or 7, and with the double wheel maybe a 4. I mean, I don't know how we can use the CFD for this double wheel configuration to see anything. But anyway, let's move on to the PRV results to get a better understanding of how the different rims and tread patterns affected the flow and why we are getting maybe these drag changes. So in figure 9, we see the experimental and CFD results of the 2 open rim configurations and the different tread patterns. I need to stress that these planes are just for one area that slices through near the bottom of the tire here, and that is important to note because while we might be quick to say that the drag reduces because of a feature we see in the planes shown here, there are still the rest of the wheels to consider. So there may be something happening elsewhere which also affects the drag. Anyway, from these figures, we can see that the CFD consistently mispredicts the separation around the tire shoulder here, which is these lower graphs here. The general pattern looks pretty good, but they are still a little off. So for example, in figure 9a, we can see that the wake of the PIV plane is more angled away from the wheel. It is sharper as opposed to the CFD, which is a little bit flatter. Alternatively, if we look at figure 9d, we see that the wake for the PIV is larger in general. And one thing I should mention is that they use 2 different color bars for the PIV compared to the CFD, which is never a good idea if you're trying to compare things. If you're trying to compare things, you should use the same color bar. So that makes it a little more difficult here to compare, but still I think we can conclude what we have just concluded here, that the wakes are generally pretty good, but they are a little bit off to some extent. So this validation section here tells me that the CFD didn't capture the flow around the shoulder of the tire as well, and maybe even how much flow is funneled down to around the contact patch near the tire and the ground because of these wakes, how they are forming down in this region. So this could easily be because of different tire shoulder sharpnesses or because of different streamline curvatures because of the test sections, and perhaps there are other reasons why the CFD is different. But anyway, let's focus on the PIV from the experiments. we can see that the first two figures are for the tire, these two here, are for the tire with just longitudinal grooves and for different rim configurations. While the last two grooves are for the exact same rims, but for the tires with the lateral grooves as well. And it's quite clear here that the lateral grooves reduce the flow separation around the tire shoulder. You can see here, for the longitudinal groove, it starts much sooner upstream, as opposed to here it's like about midway. So that makes sense, because if you think about the grooves, when you have these lateral grooves meeting the edge of the tire, they're effectively making this edge, the shoulder at this point, have a larger radius of curvature, which means that they are more rounded. Comparing that to the spaces between the two lateral grooves, that edge is much sharper and has a much smaller radius of curvature. That radius of curvature greatly determines whether the flow will stay attached or not, with a smaller radius meaning a sharper edge, resulting in the flow more likely to separate. So I would be comfortable in concluding that the lateral grooves here are making the flow stay attached around the shoulder more, which in part, at least, is responsible for the drag reduction. Now, it could also be that the lateral grooves are funneling more air down here and maybe making the wake a little bit less wakey, but we don't really know that from these this data here. Now, that makes things more complicated because the flow attachment is usually accompanied with a drop in drag in this region, and if there is a drop in drag here, then there probably is going to be a really large increase somewhere else, or a general increase in drag across a larger region, because from table 1, we saw that the lateral grooves adds a lot of drag. So that is something to further investigate. Now let's move on to the ventilation drag. So I must say that the way they tried to decouple the ventilation drag from the rest of the drag of the wheels is a little dodgy, and by little dodgy, I mean a lot dodgy. They used their CFD setup to then compare the values to the experiments and then determine what the ventilation drag was, given that they weren't able to directly measure the ventilation drag in the experiments. So they tested a few different setups, as we see here, as we have like single wheel, then double wheel, then single wheel, and then with different rims and tread patterns. So unfortunately, each setup has this double configuration in there. And the reason why I don't like that is because the CFD was passable for the single wheel, but as soon as we went to the double wheel, well, I don't think the results are that accurate. So that makes the total results of this section not very trustworthy. Anyway, just as general interest, let's just go through what they were talking about here. What they found was that the longitudinal grooves added quite a lot of additional ventilation drag, and the lateral grooves added more than double, according to the CFD wind tunnel hybrid approach. So here we see in this table 4 here, setup 2 compared to setup 1 was 58% increase, and setup 2 here we had treaded like the lateral grooves on the 2 double wheel here, and then for setup 3 we had lateral grooves across the entire range, and when we put more lateral grooves on, we get a lot more ventilation drag. And that is quite interesting, that such a small feature such as these lateral grooves can add so much to the drag. And again, this is the CFD added into this, so I'm not sure if this is completely accurate, but I'm pretty sure the trend is generally true. I mean, we're seeing that as we add more lateral grooves on, we're getting more and more drag, and it's just interesting to see because it kind of makes sense that these lateral grooves are chopping through the air, so that's going to result in a lot of resistance backwards for the wheel. That means that the engine has to produce more torque to overcome this resistance force. That's the drag. So that is a pretty cool result, and that brings us to the end of this podcast. So it was a long one, but I liked it, and if you liked it as well, hit the like button and subscribe or follow button depending on what platform you're on, and check out our CFD courses and MSP Hawk to make your experiments more accurate. Links in the description below, and I'll see you next podcast. Peace out, amigos.